The Ordovician Ocean was thriving. For 40 million years, life had been diversifying faster than at any other point in Earth's history, building reefs, evolving armor, filling every available niche in shallow tropical seas that covered half the continents. Then, in less than 2 million years, 85% of it died. Not from an asteroid, not from a supervolcano. The planet's own thermostat broke, and when it tried to fix itself, the cure was worse than the disease. This is the story of how ocean circulation, the engine that keeps marine life alive, can catastrophically fail, and why the evidence buried in rocks tells us that recovery itself can kill. The late Ordovician mass extinction sits in the fossil record as the second deadliest event in planetary history. Roughly 85% of all marine species vanished. Between 50 and 60% of the genera disappeared. A quarter of all families were erased. The killing concentrated in a geological instant called the Hernantian stage, which lasted only about 1.4 million years. A blink in deep time, but long enough to dismantle an entire world. This wasn't a land extinction. There was almost nothing on land to kill. No trees existed, no grasses, no flowers, no vertebrates walking around. The continents were gray and reddish-brown, covered only by primitive mosses, liverworts, and perhaps a few millipede-like arthropods crawling over bare rock. All the oxygen in Earth's atmosphere came from the ocean, not forests. All the biodiversity, all the evolutionary experimentation, all the complexity, it was underwater. So the question becomes specific. How do you suffocate an ocean that makes the planet's oxygen? How do you kill the filter feeders, the reef builders, the apex predators, the drifting plankton, all at once, globally, in a coordinated collapse? The answer involves continents drifting to the wrong latitude, mountains scrubbing the atmosphere clean of carbon dioxide, and ocean circulation grinding to a halt. But it wasn't one disaster, it was two. Before the fall, the Ordovician period was a greenhouse world. Sea levels sat roughly 200 meters higher than today. A single massive ocean called Panthalassa covered the northern hemisphere. But what made the Ordovician special were the shallow continental seas, tropical, sun-drenched waters spreading across what would become North America and Northern Europe. These weren't deep abyssal zones. They were warm, clear, oxygenated shelves, essentially planetary aquariums where life could explode in diversity. This explosion had a name, the Great Ordovician Biodiversification Event. While the earlier Cambrian explosion had created the major body plans, the phyla, the Ordovician was when life filled in the details. It was the most sustained increase in biodiversity Earth has ever seen. And, unlike modern oceans dominated by fish, the Ordovician was ruled by a different caste. The apex predators were orthocone nautiloids, giant cephalopods with straight cone-shaped shells reaching lengths of 6 to 9 meters. Camaracaras was the most famous. They had tentacles and a beak protruding from the front of their shells, and they likely moved through the water column using jet propulsion, snatching up trilobites and early fish. They were the submarines of the ancient world, floating neutrally buoyant through tropical waters, adjusting their depth by controlling gas and fluid in their chambered shells. Trilobites covered the seafloor in extraordinary diversity. By the Ordovician, they had become the dominant arthropods of the ocean bottom, the bugs of the ancient seafloor. Some species had evolved elaborate spines for defense against the hunting orthocones. Others, like Asaphus, developed eyes on stalks so they could bury themselves in sediment while watching for predators. Their eyes were made of calcite crystal lenses, rigid structures that gave them excellent depth perception and motion detection. When threatened, certain trilobites could roll up completely, a behavior called enrollment, tucking their softer undersides into an armored ball. The seafloor itself was covered in crinoids, sea lilies that looked like plants but were actually echinoderms, relatives of starfish. They created vast underwater meadows, their feathery arms filtering food particles from the current. These meadows were so dense in some areas that their fossil remains form entire limestone beds meters thick. Alongside them were the reef builders, tabulate and rugose corals, constructing massive calcified structures, and stromatoporoids, hard, sponge-like creatures that cemented everything together, creating the framework that held the reef structure solid against currents and storms. Fixed organisms dominated the Ordovician seafloor. Brachiopods and bryozoans filtered water through their bodies. The biological filtration capacity was immense, keeping many areas of the ocean clearer than they are today, allowing sunlight to penetrate deeper and fuel more photosynthesis. Floating above all this were the graptolites, colonial organisms that look like hacksaw blades, or spirals drifting in the plankton. Because they drifted globally on ocean currents, they spread worldwide rapidly. When a new species evolved, it appeared in rocks on different continents at the same time. This makes them perfect index fossils for dating Ordovician rocks with precision. When graptolites die off in the fossil record, we know something global has happened. Early vertebrates existed but hadn't yet taken over. Conodonts were eel-like animals, known mostly from their microscopic teeth. The animals themselves were soft-bodied and rarely fossilized, but their teeth are everywhere in Ordovician rocks. Ostracoderms were heavily armored, jawless fish, slow bottom feeders covered in bony plates, sucking up sediment and straining it for organic matter. They were tanks, not hunters, grinding slowly across the seafloor, with mouths that couldn't bite or grasp. For 40 million years, this system worked. Evolution had invested heavily in shells, spines, and calcified defenses. Specialization was the winning strategy. The setup for the extinction was geographic. The supercontinent Gondwana, comprising what would become South America, Africa, Antarctica, Australia, and India, was drifting southward. By the late Ordovician, Gondwana sat squarely over the South Pole. This matters because land holds ice better than water. Ocean water can't build thick ice sheets because it's constantly moving and carrying heat. But land provides a stable platform where snow can accumulate year after year, compressing into glacial ice kilometers thick. Having a continent positioned over a pole is a prerequisite for building the massive ice sheets that can alter the global climate. At the same time, a mountain building event was occurring in what is now eastern North America. The tectonic orogeny was the result of tectonic collision, an island arc smashing into the edge of the North American continent. This created a mountain range rivaling the modern Himalayas in scale, with peaks possibly reaching 5 to 6 kilometers high. Fresh rock exposed to the atmosphere began a chemical reaction that would change the planet. Rain dissolves carbon dioxide from the air, forming weak carbonic acid. When this acidic rain hits silicate rock, rocks containing silicon and oxygen, bonded with metals like calcium or magnesium, it weathers the stone. The acid breaks down the minerals, releasing calcium and bicarbonate ions that wash into rivers and eventually reach the ocean. There, marine organisms use these ions to build shells and skeletons made of calcium carbonate. When these organisms die, their shells sink and accumulate as limestone on the seafloor. The carbon that was once atmospheric CO2 is now locked in solid rock, removed from the atmosphere for millions of years. Under normal conditions, this weathering process balances the carbon cycle. Volcanoes pump CO2 into the atmosphere through eruptions and outgassing at mid-ocean ridges. Weathering removes it. The two processes reach equilibrium, keeping atmospheric CO2 levels relatively stable over geological time. But the tectonic mountains expose so much fresh rock, and weathering rates accelerate with increased surface area and higher elevations, that the balance tipped. The removal rate exceeded the input rate. Atmospheric CO2 levels plummeted. The evidence for this collapse sits in limestone from the Hernantian stage. Carbon comes in two stable isotopes, carbon-12, which is lighter, and carbon-13, which is heavier. Life prefers carbon-12 because it requires slightly less energy to incorporate into organic molecules. So when photosynthetic organisms are thriving and burying large amounts of organic matter, they lock up the light carbon preferentially. The heavy carbon-13 gets left behind in the water and incorporated into carbonate rocks forming on the seafloor. In Hernantian limestone, carbon-13 levels spike dramatically, a positive excursion in the isotope record. This tells us that the carbon cycle underwent a massive disruption, likely from both increased organic burial and the chemical weathering of all that fresh mountain rock scrubbing CO2 CO2 from the atmosphere. With CO2 scrubbed from the atmosphere, Earth began to cool. The greenhouse effect weakened. Temperatures dropped at the poles first, where seasonal darkness already limited solar heating. Ice started forming on Gondwana. Once ice forms, it reflects sunlight back into space, the albedo effect. Fresh snow reflects about 80 to 90% of incoming solar radiation compared to ocean water, which absorbs most of it. More ice means more reflection, which means less solar energy absorbed, which means more cooling, which means more ice formation. The feedback loop accelerated. What started as a gradual cooling became a runaway process. Within perhaps tens of thousands of years, massive ice sheets covered southern Gondwana, locking up enormous volumes of water. As water froze into ice sheets on Gondwana, global sea levels fell. The estimates range from 80 to 150 meters, a drop large enough to expose vast stretches of the continental shelves where most marine life lived. The shallow tropical seas that had been the engine of biodiversity simply drained away. For sessile organisms, the ones that couldn't move, this was a death sentence. Corals, sponges, and brachiopods that had been anchored to the seafloor in warm, sunlit water were suddenly exposed to air. Reefs that had taken millions of years to build dried out. Stromatoporoids, the cement of the ancient reefs, couldn't survive on land. The tabulate and rugose corals that had built massive structures simply died where they stood as the water receded around them. Mobile organisms weren't much better off. Trilobites and early fish were forced into deeper, darker water as their shallow habitats vanished. But deeper water was colder and had less light for photosynthesis, which meant less food at the base of the food web. The planktonic organisms faced their own crisis. Graptolites drifting in the surface waters were adapted to tropical temperatures. They had evolved during 40 million years of greenhouse conditions and had no evolutionary experience with cold. As surface waters cooled, these stenothermal organisms, species with narrow temperature tolerances, had nowhere to migrate. The poles were freezing. The equatorial regions were cooling. There was no refuge of warm water left anywhere on the planet. They were trapped between vanishing habitat and incompatible temperatures. The orthocone nautiloids, the giant apex predators that had ruled the Ordovician seas, began to disappear. Large body size is a liability in mass extinctions. Big animals need more food, more stable conditions, more space. Their long generation times mean they can't adapt quickly to changing environments. When habitats shrink and food webs collapse, the giants die first. Camaracaras and its relatives, the 9-meter submarines of the ancient ocean, couldn't find enough prey in the shrinking, cooling seas. For a time, the deep ocean remained relatively healthy. Cold water at the poles became denser and sank, driving deep ocean circulation. This cold, oxygenated water moved along the bottom, the thermohaline circulation that keeps modern oceans alive. It kept the abyssal zones livable during the glaciation, but the surface world, the shelves, the reefs, the sunny shallows where biodiversity had concentrated, was devastated. Geologists have found evidence in the rocks. Bioturbation decreases sharply during this period. Bioturbation is the churning of sediment by burrowing organisms, worms, arthropods, mollusks, digging through mud and sand. When these organisms are alive and active, they mix the sediment layers, creating a churned, homogenized texture. When bioturbation stops, sediment layers remain flat and laminated, preserving thin bands of different materials that weren't disrupted. The Hernantian sediments show this lamination. The worms and burrowers died, and the seafloor went quiet. The Ice Age didn't last. After perhaps 500,000 to a million years, the system reversed. The cause remains debated, but volcanic activity likely played a role. Geologists have found spikes of mercury in Ordovician rocks from this period, specifically in sections from present-day Nevada, South China, and Scotland. Volcanoes emit mercury as a trace gas during eruptions. Mercury gets deposited globally through the atmosphere, so spikes in multiple locations simultaneously suggest massive volcanic events. These mercury anomalies point to a large igneous province, a volcanic event where millions of cubic kilometers of lava flood across the landscape, releasing enormous quantities of CO2 and other gases. Such an event may have pumped enough greenhouse gas back into the atmosphere to overwhelm the weathering process and trigger rapid warming. The warming was geologically rapid. The glaciers on Gondwana began to melt, dumping enormous volumes of fresh water into the oceans. Fresh water has lower density than salt water because it lacks dissolved salts and minerals. When you pour fresh water into salt water, it sits on top. This created a stratified ocean, a layer of relatively fresh water floating above the heavier salt water below, with a sharp boundary between them called a halocline. Normally, ocean circulation involves vertical mixing. Cold, dense water sinks at the poles and flows along the bottom toward the equator. In other regions, warmer surface water moves poleward to replace it. Eventually, the deep water rises back to the surface, a process called upwelling, bringing nutrients and oxygen with it. This overturning circulation is what keeps the ocean alive. It delivers oxygen to the depths and brings nutrients to the surface where photosynthesis happens. But when the surface layer is capped with fresh water, this circulation stops. The density difference between the fresh surface layer and the salty deep layer becomes too great for wind and temperature differences to overcome. The stratification acts as a barrier. The vertical currents that had been mixing the ocean for millions of years simply halted. The engines stalled. Without vertical mixing, the deep ocean lost its oxygen supply. Oxygen enters seawater at the surface through contact with the atmosphere and through photosynthesis by marine algae. In a mixed ocean, this oxygen gets carried to depth by sinking water, but in a stratified ocean, the oxygen stays trapped in the surface layer. Meanwhile, organic matter from the surface, dead plankton, fecal pellets, marine snow, continues to sink and decompose in the deep water. Decomposition consumes oxygen. As bacteria and other organisms break down organic material, they use up whatever oxygen is present. With no fresh supply coming down from above, the deep waters went anoxic, completely devoid of oxygen. In an oxygen-free environment, different bacteria take over. Anaerobic bacteria don't breathe oxygen. Instead, many of them use sulfate, a molecule abundant in seawater, as an electron acceptor in their metabolism. The waste product of this process is hydrogen sulfide. Hydrogen sulfide is toxic. In high concentrations, it binds to the iron in hemoglobin and cytochromes, shutting down cellular respiration in any organism that encounters it. It's the rotten egg smell of swamps and sewers. But in the deep Ordovician ocean, it built up to lethal concentrations. This condition, an anoxic ocean saturated with hydrogen sulfide, is called euxinia. The water in euxinic zones often appears purple or green due to photosynthetic sulfur bacteria living in the toxic layer where a little light penetrates. These bacteria use hydrogen sulfide instead of water for photosynthesis, and their pigments give the water its characteristic color. Chemists can detect ancient euxinia by looking for specific sulfur compounds preserved in rocks, particularly pyrite framboids and certain organic sulfur molecules, and for iron minerals that only form in sulfide-rich conditions. These markers are found in Hernantian sediments worldwide. There's more evidence. Fossils of chitinozoans, microscopic plankton with organic walled shells, and plant spores from this period show deformities and malformations. Individuals appear misshapen, with irregular growth patterns and abnormal structures. These abnormalities indicate exposure to heavy metals like lead, arsenic, and iron. In anoxic conditions, these metals become mobilized from sediments and dissolved into the water column. The malformed fossils are evidence that the ocean chemistry had become toxic, not just from hydrogen sulfide, but from a cocktail of dissolved metals. As the glaciers melted and sea levels rose again, the reef-flooded continental shelves should have been a refuge. Survivors of the freeze should have been able to repopulate the shallow seas. But the water that flooded back wasn't the warm, clear, oxygenated water of the greenhouse Ordovician. It was warm, yes, but it was also anoxic and saturated with hydrogen sulfide. The toxic water that had been confined to the stratified deep ocean rose up onto the shelves. The mechanism was straightforward. As sea levels levels rose, the anoxic deep water simply expanded upward and outward, flooding into the newly submerged coastal areas. Organisms that had adapted to cold, that had survived the habitat loss and the thermal shock, now drowned in poison. Brachiopods, which had already suffered massive losses during the glaciation, were hit again. The orthid brachiopods, a major group that had been abundant throughout the early and middle Ordovician, were particularly decimated. Their diversity collapsed, and they never recovered their former prominence. Trilobites lost more than half of their families during this second pulse. Entire lineages vanished. They had spent the last 40 million years evolving thicker shells, better eyes, defensive spines, elaborate calcified structures designed to survive predation. None of it mattered against dissolved hydrogen sulfide. Graptolites, which had been among the most abundant and diverse organisms in the Ordovician Ocean, were nearly wiped out. Species that had drifted globally, that had colonized every ocean basin, disappeared from the fossil record almost simultaneously worldwide. Only a handful of species survived to repopulate the Silurian. The index fossils that had been so useful for dating Ordovician rocks suddenly became rare and limited in diversity. Conodonts, the early vertebrates, known mostly from their microscopic teeth, lost roughly 80% of their species. The fossil teeth show a dramatic drop in diversity and abundance in Hernantian rocks. The great coral reef systems collapsed entirely. The tabulate and rugose corals that had built massive structures across the tropical shelves disappeared from the fossil record. The reefs they had constructed became fossil graveyards, layers of dead coral skeletons without the living organisms to continue building. It would take millions of years, well into the Silurian and Devonian periods, for reef ecosystems to develop again on a comparable scale. The orthocone nautiloids, the giants of the Ordovician, were reduced to a fraction of their former diversity. Camarasaurus and most of its giant relatives vanished. The long, straight-shelled apex predators that had ruled the water column for tens of millions of years never regained their dominance. Some nautiloid lineages survived, coiled forms that were smaller and more adaptable, but the age of the giant orthocone was over. Not everything died. About 15% of species made it through both pulses. The survivors followed a pattern. Generalists, organisms with wide temperature tolerance and flexible diets, fared better than specialists. Species that could tolerate a range of temperatures, that could eat different types of food, that could live in various depths, had options when conditions changed. The specialists, perfectly adapted to specific conditions, had nowhere to go when those conditions vanished. Deepwater organisms that were already adapted to low oxygen environments survived more often than those from the oxygenated surface. Certain bivalves and other mollusks that had lived in oxygen minimum zones, areas where oxygen levels were naturally low, already had the physiology to survive anoxic or near anoxic conditions. When the rest of the ocean went anoxic, they had an advantage. Smaller creatures outlasted giants. Size, specialization, and narrow environmental tolerance were liabilities. An organism that weighed kilograms needed vastly more food and resources than one that weighed grams. When food webs collapsed and habitats shrank, being small was an asset. Flexibility was survival. The Silurian period began with what paleontologists call disaster taxa, fast reproducing organisms that can colonize disturbed environments quickly. These are the weeds of the ancient ocean, filling empty ecological space before more specialized forms can evolve. Small generalist brachiopods and bivalves spread rapidly. Simple opportunistic organisms dominated the early Silurian seafloor. The world was reset. But the reset created opportunities. With the giant orthocones reduced in number, vertebrates had room to evolve. The Silurian saw the evolution of jaws in fish, hinged structures that could bite and grasp, not just suck and filter. This was a turning point. The Ordovician Ocean had been dominated by tentacles, grabbing, filter feeders straining, and sucker mouths rasping. The post-extinction ocean became a world of biting and grasping. Jawed fish changed the rules, and eventually their descendants, amphibians, reptiles, mammals, would colonize land and dominate the planet. Life also began a serious invasion of land during the Silurian. Cooksonia, the first plant with true vascular tissue and upright stalks, appeared in the fossil record. Arthropods followed, millipedes, primitive arachnids, eventually insects. The timing suggests the Ordovician extinction may have cleared ecological space or created evolutionary pressure that accelerated the move onto land. The ocean had become crowded, dangerous, and unpredictable. The barren continents represented empty niches. There's an irony buried in the rocks. Some researchers have suggested that the very mosses and primitive plants that were colonizing land during the Ordovician may have contributed to the extinction. Plant roots and the organic acids they secrete chemically weather rock more efficiently than rain alone, releasing phosphorus into rivers that flow to the ocean. Phosphorus fertilizes algae. Algae blooms consume oxygen when they decompose. The same process happening today in agricultural runoff, eutrophication, may have been triggered hundreds of millions of years ago by life's first steps onto land. The pioneers may have accidentally poisoned the sea they came. We live in a warming world where ocean circulation is slowing. The Atlantic meridional overturning circulation, the system that moves warm surface water north and cold deep water south, has weakened by about 15% since the mid-20th century. Deoxygenated dead zones are expanding in coastal waters worldwide, particularly in areas with high nutrient runoff. The mechanisms aren't identical to the Ordovician, but the components are familiar. Temperature shifts, circulation changes, oxygen loss, and stratification from freshwater inputs. The Ordovician teaches us that planetary thermostat failures don't come with single causes or simple solutions. Mountains rise, CO2 drops, ice forms, circulation changes, chemistry shifts. Each piece triggers the next in a cascade that no single organism or ecosystem can prepare for, and it teaches us that survival isn't guaranteed by dominance or complexity. The giants die, the specialists die. The flexible and small endure, but even they inherit a diminished world that takes millions of years to rebuild. 445 million years later, the rocks still hold the evidence. Isotope spikes in limestone, recording the carbon cycle collapse. Glacial scars in the Sahara, proving polar ice. Mercury traces from ancient volcanoes. Malformed fossils, recording toxic water. The ocean's engine stalled once. It restarted, but 85% of what had been thriving before the stall never came back. The Ordovician was paradise, then it was ice, then it was poison. What survived did so not through strength or specialization, but through the luck of being flexible enough to endure both.